Hey, Mr. Gretto here. Purpose of this lecture is to give you information from the first lecture of the unit, how we organize elements on the periodic table. Alright, so this is the note packet that you guys should have access to and be following along with. Unit 4, Lecture 1. Periodic table at the bottom. Alright, so let's get into it. So during this lecture, we want to learn about how elements are organized in the modern periodic table, and also go into a little bit of history and learn about our father of the periodic table, Dmitry Ivanovich Mendeleev. Alright, so there's basically three main steps I want you guys to focus on when we talk about how the periodic table is developed. Elements were really known about in the 1700s. There's like 13 elements they knew in the 1700s. As time went on, we had better techniques, better able to isolate elements, better able to discover them, things like that. When we first start to organize them, though, that's where triads came into play. So here are what triads kind of look like. The main scientist of this was J.W. Berinier. I butchered that name, I'm so sorry. But that's not the point. So triads were in 1829, and they literally grouped elements based on similar properties. So here's kind of our modern periodic table, our triads. So lithium, sodium, potassium were one of the triads that were made up. And they're based on their physical and chemical properties. These are the guys that blow up in water, literally catch fire. It's kind of cool. So they're based on their similar properties and grouped. Another cool thing about them is you kind of use the first and the last of the triad to guesstimate the mass of the middle guy. So you add them and divide it by 2, found the average, then you'd get the mass of the middle guy, which is pretty cool. Alright, so triads didn't work out terribly well though, just because as time went on we found more elements. So you can see the calcium, strontium, barium group. We had beryllium and magnesium in there also. We start to figure out that there's more like quintuplets, and quintuplets just didn't sound as cool. So as we discovered more elements, the triads kind of broke down, which is where Dmitry Mendeleev comes into play. Alright, so this is our second big time period of organizing elements. And Dmitry Mendeleev still kind of had the triads together. So here we see that last triad, the chlorine, bromine, and iodine. These guys down here. You can still see that they're still in the same row. So we kind of group the triads in the same row, except for it's not just the triads, there are other elements in there too. So we start to have more than just 3 elements. This is kind of like our modern periodic table, but flipped sideways, right? What is a row here is now a column in our table. But some important things Dmitry Mendeleev did. He organized the elements into this big, cool table. And not only did he organize it by mass, so you can see how it's an increasing atomic mass, 24, 27, 28. He left big gaps in the periodic table. And that's why Dmitry Mendeleev was so important, why his periodic table was accepted more than a scientist who put forth the same idea around the same time. So there's a guy named Lothar Meyer who had almost an identical periodic table to this. But his wasn't accepted as much as Dmitry Mendeleev's because Mendeleev left these gaps, published them a little sooner, and he did something pretty cool. He made risky predictions about these gaps. So here you can see 2 question marks, right? They're right between zinc and arsenic. If you look at your modern periodic table, you'll see that the 2 missing elements are gallium and germanium, respectively. What was cool about Dmitry Mendeleev is he made that prediction that, 1, these 2 elements exist. Sorry, I lost my mouse for a second. And 2, he predicted a lot of their properties based on their groups. So he said that this element should have an atomic mass around 68 atomic mass units. This guy should be around 70 atomic mass units, which is pretty close to our modern periodic table one. So he made those predictions, and he was fairly accurate with them, which gives his periodic table a lot of validation. All right. So those are the key ideas about Dmitry Mendeleev's table. One other thing I might want to point out, see, I told you earlier that's in order of increasing atomic mass. He did switch around some things, like he knew that telluranium was better with selenium, so he kind of switched this order up here, 128 and then 127. It's a pretty smart move because eventually, once we figure out that atomic mass doesn't work as well as its atomic number, these will be in this order, telluranium followed by iodine. So that brings us to our modern periodic table. I know this one probably looks a little weird. It's because we put that lanthanide and actinide series, those f orbital elements, into the actual stretched out periodic table. Most of the time you don't see the periodic table like this just because it takes up a lot of space. You'll see it more likely like this guy over here. Those long elements in here get dropped down to underneath the periodic table. But know that they are part of the big table. They are stretched out like that. The periodic table is supposed to be stretched out like that. It's just much easier to view in this form than in this form. Alright, so now we have our modern periodic table, which still kind of has elements from both the triads and Dmitry Mendeleev's sideways table. For the triads nowadays, we have elements organized into groups, also known as families. And that's where like the similar properties come into play. Lithium, sodium, potassium are all still together in that order. For Dmitry Mendeleev's table, we have those missing elements filled in. Gallium, germanium, telluranium, and iodine are in the correct order. But instead of organizing it by average atomic mass, we do it by atomic number, which is the same thing as the number of protons. Now if you remember, Mendeleev published tables in 1869. The proton wasn't actually discovered until 1920, so this was 30 some years before that. Alright, so our table with the average atomic number, or using the atomic number, it was discovered after 1920 because we need to know what the protons were. So now our modern table is organized by atomic number of protons. 1 proton, 2 proton, 3, 4, 79 protons in gold. Hey you, what are you doing with my gold chain? Alright, so the last thing from that first lecture that we want to talk about is there's going to be 3 broad groups of elements. As you can see, there are a lot of different groups of elements, but there's going to be 3 broad categories, and they are metals, metalloids, and nonmetals. Right? When you think of a metal, you think of different properties like something shiny, a shield, or things like that. That's what I think of when I think of metals. You might also think of like wires and things like that. Those are what these guys are all going to be about. So your metals are things that are elements that can conduct electricity, that are typically shiny, hard, solids, that are, fancy words, malleable and ductile. So malleable refers to something being able to be hammered into thin sheets. So when you apply pressure, it like stretches out into a thin sheet. Where ductile tells you can like pull it into wires, which are awesome properties for metals because then we can utilize them in a lot of different ways. A nonmetal, kind of the name gives away, is almost the exact opposite of a metal. Right, so the nonmetals are all over here. Where these guys were nice and hard and shiny, these are kind of brittle and rarely have like a high luster. Now there's a lot of variety and properties in the nonmetals, so some of them might be harder and things like that. Like carbon is made up of, or part of diamonds, and extremely hard. But in general, they don't conduct electricity and things like that. They aren't the same as the metals. They have the opposite properties. Which brings us to the metalloids. This is a weird group because the metalloids are kind of both metals and non-metals at the same time. I kind of think of androids, which are both robots and humans at the same time. Like an android. So a metalloid is both a nut metal and a non-metal. It just depends on the conditions that they're under, whether they can conduct electricity or whether they'll be malleable and things like that. I think silicon is the main example that people use, where silicon typically doesn't conduct electricity. But if you put it under the right conditions, like mixing it with a little bit of bromine, then it becomes a great conductor. So It all depends on the conditions for the metalloid. It can have both properties of metals and nonmetals. You also might see one other weird thing on the periodic table. Hydrogen is all the way over here. It's technically a nonmetal also, so even though it's on the left side, it's the only one on the left side that acts like a nonmetal. So our metalloid splits the line. Everything on the left is metal. Everything on the right is a nonmetal. The exception is the hydrogen. All right. So that's some of the key ideas from Lecture 1, which you guys should have all checked out. Okay. I'll see you for Lecture 2. Catch you guys later. Where's the...